Get 2 bags.
All right, so this week we're going to start where we left off last time. We made a good clean break last time, actually. We covered Nmap, HPing2, some other host discovery. We're still in host discovery, so to give kind of a big picture, we're looking at the 5 stages of pen testing leading up to a web pen test. We skipped passive reconnaissance because you need a connection to the internet. That's basically all about asking Google, GXFR, LinkedIn, Facebook, asking all those different internet sources about a company or a customer, who is, things like that. And we started with the active reconnaissance, where you're actually sending packets to the customer. And so we covered host discovery up to this point. We're going to continue with host discovery. So this month is Traceroute and Scapy. And so I'll start with the Traceroute that is in Windows. I think it's Traceroute is the command. And let's see what we can find. Okay, so it's their IPs. So on this particular Windows machine, we need to kind of remember that this machine is 102. Hopefully everybody can see that all right. And that means that the Linux box must be 101, since the way that VirtualBox assigns IPs and its DHCP by default is starting at 101 and going up from there. Whichever one starts at first wins and gets to 101, and then the second one grabs 102 and so on. Okay, so we did a trace route out to 101, so since that seems to be working, let's go over to the Linux. And let's see if we can listen for that connection. That'll let us look at the trace route a little bit easier. Okay, so start TCP dump. Just listening on, well, it looks like it's going to listen on ETH1. It auto-detected that card. Go back to Windows, try the Traceroute again, and go back to Linux and see if it heard us. Okay, looks like it did. So here's the packets that were sent by Windows. So Windows sent a ICMP. You can see that here. Came from 102 to 101, of course, is how to read this part. And the type of packet, specifically here, is an ICMP echo request. We responded from Linux's point of view. We replied with ICMP echo replies. So you can see how the Windows traceroute works is essentially it implements pings, and it and it tries to ping its way along the route to the host, and it counts the number of hops along the way. Now sometimes you'll see Windows with the little stars for the IP address in the middle of a scan, and then eventually it gets to the target and it actually reveals the final number of hops. But that means the intervening boxes didn't have the ICMP enabled, but the final target did.
Okay. In this case, it's using UDP since it's on a Linux box.
Well, we did the traceroute from Windows, from this Windows XP here, okay. And it's limited to using ICMP.
Okay.
So the traceroute.
What was the other?
Traceroute in Windows is limited to just doing ICMPs, and that's kind of the problem. So that's actually the problem statement we're going to work from today.
Okay. What was the other traffic that was UDP that was coming up on?
Well, my Linux box is chit-chatting, or else the Windows box is chit-chatting on some other protocol. To be honest, actually, I kind of ignored that. It looks like it is it's a NetBIOS.
Oh.
Oh, yeah. It is my VirtualBox host, C156.1, talking on port 137 UDP. It's doing NetBIOS discovery protocols, I believe. I think it's asking if anyone's out there is what it's doing. So we could fix that. If we go back to the Linux, okay, kill this. Control L. Oops, there we go. Okay, so we can say host is 192.168.56.101, and I think or is just or. Okay. TCP dump uses the, I think it's called Berkeley Packet Filters, BDP protocol, to describe how you want to filter the packets out. And so you can just type that syntax in and get it to only listens. That should keep it from listening to the host. All right, so the traceroute worked. What's the problem? Well, it worked on this particular network because the backtrack box I have set up has no firewall, and it's also willing to respond on ICMP. But that's fairly unusual in corporate networks today. Most devices are going to have ICMP turned off. Even if the hosts are running it, the routers that sit between the subnets are going to block it. They're not going to pass the packets on, so even if the host had it enabled, you're still not going to be able to trace route. So one of the things we can do is we can use different kinds of trace routes to get around these restrictions. Also, ICMP packets don't traverse the internet very well. There's all kinds of intervening routers, gateways along the way that are going to block these. Most firewalls, I think, are configured to block ICMP for the most part. External facing firewalls. So let's go over and look at Linux. Actually, let's configure this Windows box while we're here anyway. So to configure, if you go to your firewall and you go to the Advanced tab and you go to the ICMP box, the one in the middle here, and click on Settings, you can control whether or not you're going to listen to ICMP here. So if we turn the Allow Incoming Echo Request box off, which I don't think I can do on this one because I believe I've got NetBIOS running over something, or I've got some program enabled. It's probably not going to let me turn that off. Let's see if I can figure out what it is. It might be file and print sharing. Let's try to disable that. Then go to advanced and see if it'll let us turn off ICMP. All right, sorry, I can't remember which program in Windows it is that makes it mandatory that ICMP echo requests absolutely have to be turned on. It could be one of these, remote management maybe. Let's try this. There we go, okay. So it was either file and printer sharing or remote management. I think it's file and printer sharing. I probably just needed to save my settings first and then go back in so that we can disable the ICMP. So that should tell the Windows firewall to act kind of like a normal corporate box and not allow us to do any kind of trace route or any kind of ping ICMP, I should say. So let's do ping 192.168.56.102 was Windows, and we'll just wait and wait. If it was going to work, it would have worked by now, but after 30 seconds, it should time out. So there was another tool that was introduced, it's been a few years now at least. It's a layer 4 traceroute, and it got around a lot of these problems because it isn't restricted to using the ICMP packets to do the trace routing. Then later, after May of last year, the Traceroute, the native Traceroute program in Linux got an upgrade and actually took on a lot of the features of the layer 4 traceroute. So now it's just sort of built in natively without the layer 4 traceroute. Now layer 4 traceroute is still an advanced trace routing tool, has a lot of options that may not necessarily be available in the regular traceroute command, but the newer Linux traceroute is really good. So we're going to work from it today. It's not TraceRT, it's spelled all the way out, Traceroute. And it has a nice menu that tells you all the options. It also has a main page and the whole 9 yards. So the basics of it is you do a trace route and then the IP address or host name of the target. Start up a separate window here. Do a TCP dump. Listen on ETH 1. Actually, we probably should check that first. If you do an ifconfig in your Linux, it'll tell you the cards that you have. ETH1 is the one associated with the VirtualBox network. It's the one with the 56 subnet in it. So -i's interface, ETH1. 2 ends. The first end says don't resolve host names. The second end is don't resolve port names. Makes everything work a little bit faster. You can be verbose with the V's up to 3 of them. And we're going to set the snap length to 0, meaning capture the entire packet. Snap length is how many bytes of the packet that you actually capture when you see the packet. And 0 just means pretty much indefinite. And we're going to do host 192.168.56.101. And or, I think you can do or host 56.102. Okay. All right, switch back over to the other window and do the traceroute. And what we're going to do is try to figure out how does traceroute work. Okay, there we go. Whoops. Must have had something wrong with my filters. Don't have time to diagnose that right now, so we're just going to listen.
You got a typo on the Traceroute.
It seems to be working. Let's take the card out of the equation. Let's try this. Let's see. 0 packets captured. Not always the way when you're trying to do a demo.
Oh, hell, demo cards.
Let's make a sacrifice first.
Sacrifice to the demo cards.
Yeah.
Does it have 2 interfaces on it?
It's got lots of interfaces.
Is your Traceroute actually using the ETH1 that the PC does one?
It has to use the one that has a route, so it'll have it's
So that's the
kind
one
of
that
forced
has
into that one. Yeah. Let's see. Just try. So we know it's listening to something. We just can't see the tracer out. Wrong IP address, maybe. Ah, there we go. Okay.
You shoot the scores.
Think outside the box, right? Okay. Let's try that again.
Think outside the virtual box?
Exactly. Okay, so it was trying like crazy to do the trace route. We can see it's basically it's going to time out. It's going to get to like 30, and then it's just going to give up. So why didn't that work? Well, if we look at what the trace route in Linux does by default, it sends from us at 101. Oh. See if we can scroll up. One second, I just want to adjust the resolution down a little bit so we can see a little bit more on the screen. That way I can get my scroll bar back. All right, here we go. So it went from us 101 and went to 102. And then the protocol was UDP and length 60. It basically just didn't really have much payload at all. And the port it tried, let's see if we can get the port 33498. And then 499, and then 33500, and you can see the pattern. It just goes on and on and on, and down here it was all the way to 33513. Now, one thing you'll notice is that it's all 101, us, sending traffic to Windows on 102. There's no 102 replying back to 101. The firewall is blocking us. The Windows firewall doesn't allow UDP packets through unless you make an exception, like on 137. For that BIOS. So the Traceroute didn't work, and this is pretty similar to the ping that we did a second ago where it didn't work either because we had purposely gone to Windows and blocked the ICMP packets by unchecking that ICMP box at the firewall. So we still haven't figured out a way to actually trace route to these boxes that are blocking most every packet. Well, we know one thing about this Windows box, or at least I do, and I'll share it with you. It's a web server. So we know that it has to be listening on port 80. But that's going to be on TCP. Well, as it turns out, the Traceroute and Linux can use different protocols. So one of the first things we're going to try is to see if we can get it to work over TCP. So let's try TCP by default. Let's clear this screen off. And see if that works. Now it looks like that did work. We've actually got our first successful trace route. Let's try to figure out what it did.
Could you send UDP to 80?
Yep, you can. It wouldn't work.
No?
There's nothing listening on 80 to UDP because web servers listen on TCP.
I don't think
But as long as it isn't blocked, should you still get
But
the whole?
You can, and actually we're gonna get to that part of the presentation where we're gonna use UDP. But if you want to go ahead and start thinking about it, you got the right idea, you just got the wrong port. So think about it. It's Windows.
Yeah,
So
yeah.
maybe by the time we get there, you tell me
Alright.
which port we should try.
Maybe 53.
It's not a Windows server, but yeah, 53 is a good one to try.
But even if the port isn't open on the remote box, as long as you get back a message, because of the whole time to live thing.
The problem is this is a fully patched Windows SP3 box. It's got the most advanced firewall that Microsoft has available on that model, and it does have the ability to silently drop packets.
Okay.
So it's not like the old
Right.
school
Where the
like
errors
Windows
still giving you
SP0,
information.
yeah, where the errors would give away information. It acts almost like it's not even there, where it just silently drops the packet with no reply at all. So if we didn't know any better and we just looked at a port that was blocked by a firewall, it would appear to us as if the host wasn't turned on or didn't exist, I guess. So we can see from the TCP dump that when you enable the TCP flag with no port option, it goes to 80 anyway. So that worked out pretty well because it is a web server and it does respond on 80. I'm sure it's no accident that the designers picked port 80. I mean, that's a good bet, right? If you're on the internet. Most boxes are probably dedicated to the web. I don't know for sure, but I bet you a high percentage of them are probably server websites. This is the same behavior that Nmap uses. It sends out 4 packets by default, and one of them happens to be a TCP 80. And then it tries 3 other kinds of packets based on what's the most likely thing to be on the internet at the time that they did their study. All right, so we got the TCP option, and that one actually did work. And the next one we're going to try is using the port flag. So if we do TCP, and then if we had said, -- port equals 80, it should give us the same results. Let's clear this out. Start it over. All kinds of information. And we should see the exact same result because we specified the port was 80.
Right.
And there it is. So 192.168.56.102, port 80. And we got the same result, no surprise. All right, so knowing that we can both set the protocol and the port, now let's go back and try to get the UDP to work. This is kind of where we were headed a second ago. One guess was port 53. That's a good guess. That's DNS. A lot of DNS servers will respond on UDP 53 unless the amount of information that needs to be transmitted is really big, and then it'll switch to TCP. But by default, it's going to be typically UDP. So let's use UDP on the trace route, but we're not going to use any port options at this time. and find out what the default is. Clear start. Wait for a second, it's going to time out because turns out Windows is blocking it. So by default, well, we can look at any of them. By default, the Traceroute is trying port 53 as it is because it pretty well knows that's the most likely packet that's going to get through. It turns out it didn't work. This Windows box is just a regular desktop. It's not a server. It's not serving DNS traffic at all. It's not a domain controller or anything like that. So unfortunately it didn't work, but we can specify the port. We should be able to get around that. So you can guess that this is what port would be a good one to try for a
157?
normal desktop.
445.
157?
445, let's try that.
157,
And it turns out that one's not going to work. Anybody notice earlier when I first started why it's not going to work? You remember what I had to do to get the ICMP?
Turn off share.
I turned off the file and printer sharing. That's 445 TCP and
143?
137. Yeah, 133. Is it 130?
No, 143.
143.
135, 137.
Yeah, I think it's 135, 137,
Yeah.
38, 39.
Alright.
So let's try 137 and see if that works. And probably none of these are going to work because I've artificially changed the box to make it a lot harder.
I think 445 was just net BIOS, even if file sharing is unenabled.
I think I'm not sure. I thought NetBIOS was the 130s, and I thought 445 was not NetBIOS.
It was file sharing, though.
Oh, it's definitely file sharing for sure, but I don't believe it's over file sharing over NetBIOS. I think it's file sharing over TCP. It's the alternative form, the newer version, if you will. All right, so to get back into Windows here, open the firewall back up, put things back the way they're supposed to be, according to default installation of Windows, as it were. Okay, so if we enable that, just do a quick experiment here. I wanted to see if that ICMP was re-enabled. Yes, okay. So it's the file and print sharing automatically allows incoming echo request on the SP3 firewall. Fun little bit of trivia, if you're actually a network administrator, might be more than trivial to you to note that. See if we get any different results. Okay, UDP 137 didn't work. Let's try 139. Oops. Looks like 139 is not going to work. We can try 445 just for fun. And it doesn't look like it'll work. So let's try TCP 445 instead. And there we go. So with the file and print sharing turned back on, TCP 445 becomes a viable option for Traceroute. So that's basically how to traceroute any box, pretty much no matter what. Now, you might be thinking, well, Nmap has the ability to not only figure out which ports are open, but it has a built-in traceroute into it. You do --trace-route, I think it is, or --traceroute. And it'll automatically figure out what port to use and go ahead and do it. So why in the world would you ever use this tool? Well, actually, I'm inclined to agree with you if you're thinking that. So I just use Nmap myself. But when you're doing traceroute, if you just want to do the traceroute and you're just trying to figure out a problem, whatever, this turns out to be a pretty handy tool. I do use it sometimes when I'm looking at individual boxes. But if I'm scanning an entire subnet, you can bet I'm going to use Nmap. I'm not going to waste time like hitting every single little box, one port at a time until we figure it out. I think the biggest benefit to using it is what it teaches you about how the boxes work and respond and how the different firewalls act, and just learning why they're doing what they're doing. Now, networking technicians probably use it all the time. They're not necessarily interested in scanning entire subnets, they just want to get their job done. So they're probably looking at a particular box, particular route, or whatever. All right, so the next thing I wanted to look at was Scapy, because sometimes it's, you need to be able to actually make your own individual packets to figure a situation out. So you may need to make a packet that goes to, say, port 80 one time, but then the very next packet you make, you might want to send to, say, 81 or 0 or some other port that you're pretty sure is closed, and then compare the two results to one another. And while the Traceroute and HPing 3 now are very, very versatile, they can't do everything, so they are limited to their coding. So it does seem that Nmap can do just about anything, but the version 5 is does have at least some limitations that Scapy doesn't have, especially in the number of protocols covered. Now, Nmap 6, I think, just came out the other day, and it is turning into more of a packet crafting type tool instead of just a scanner. Plus, I think the NSE engine's been updated as well. So that one might actually be quite a bit different. For Scapy, to start it up, you just type in Scapy and hit enter. Let's see, and it gives you a little command prompt with the 3 blue arrows. The way this works is you build the packet up sort of like Lego blocks, and you're allowed to build completely nonsensical stuff that makes absolutely no sense at all. You can take a TCP packet and put an IP packet in it, for example, so it's, in other words, it's backwards. You can do anything you want because you're totally crafting the packet, and then you can just send it and see what happens. As far as learning, pen testing methods, network pen testing methods, as far as, packet crafting, this is the best tool I've seen. A few of the commands that you'll need just to kind of get started is ls. Notice that there's brackets. This is an actual function call. It's not just a command call, because we're on I guess we're on like a Python shell when we're in Scapy. So if you hit ls, there's this huge number of protocols that comes up, and these are the protocols that are supported by Scapy. So remember earlier I said Nmap can't do literally everything that Scapy can do, and that's because Scapy supports more protocols. Now with the Nmap scripting engine, Nmap supports a lot more protocols than you would think, and it can talk some high-level protocols like web and file and printer sharing and things like that as well. So it's not completely bound to TCP, UDP, but certainly you can see this list is pretty impressive. All right. Now, once you pick out your protocol, so let's say TCP, you can pass that protocol in as an argument to the ls command. So instead of giving you the big list of protocols, it'll drill down into that one protocol and give you all the attributes, if you will. These protocols, like everything else in Scapy, kind of work like objects in object-oriented programming. Things have this idea of attributes or properties, and they also have this concept of methods. But you can also sort of call functions on things too, so it's not exactly a great analogy, but it's pretty accurate. We can see that a TCP packet has attributes of source and destination ports, all the flags, and you can even set the individual attributes like the windows and seek and ACK and all those. And those are pretty important if you're trying to craft handshakes and things. You need to be able to manipulate the sequence of ACKs and things like that. All right, another command is lsc. Instead of listing protocols, this one lists commands. So even ls itself is one of the commands listed by lsc. Now with just these two commands, you can pretty well get your bearings inside of Scapy and figure out what it is you want to do. So those are the two most important ones to know. And just like LS, if you do LSC and then you do, say, pass it LS as an argument. Oops, sorry. I think maybe it was help. It's the command I'm trying to think of. Let me try that. Ah, yes, there we go. Okay, so if you use help and then pass the command as an argument into that, it'll give you a little bit more information about the individual command. Okay, so we've covered help, LS, and LSC. And the commands that we're basically going to use is SR, that's a key one, that's send and receive. And there's some variations like SR1, which will send a packet and only listen to the first response and stuff like that. There's SR loop, which, just like it sounds like, it'll send and receive over and over and over again, things like that. So we're just going to focus on just the SR for today, though. Okay, how to build a packet. Well, essentially, you don't really need to know Python. You just need to know how to put the Legos together. So we're going to have a variable packet, and we're going to set that equal to, let's say, an IP packet. So it's IP is the protocol name. We could have figured that out if we had done an LS and just looked through the list. It was in there. And then we have the brackets, open and close paren. And that'll assign an IP packet to the packet variable. And if we just type packet and hit enter, we can see that there is an IP packet inside of the variable packet. There's a method, show, which gives a lot more information. It breaks the IP packet assigned to packet down into those individual fields. These are the fields that we would have seen if we had done an LS and then passed IP in to the LS command. And we can, here with the show command though, we can see that there's the default values are set. So the version is automatically set to version 4. So IPv4 in other words, not IPv6. And then they have all these other flags, type of service and all that stuff. The most important ones, of course, are source and destination for our purposes. Now the destination of, well, us, is not going to be very useful. So let's change the destination. So instead of packet equals IP with all the defaults, we can say that the DST, which I'm reading that from right here, DST is equal to 192.168.56.102. That's the Windows box, and close paren. So if we do a packet.show now, we can see that the destination is changed. And another interesting thing, if we go back and look up here, see how the source by default is 127.0.0.1, but when we changed just the destination only, Scapy was smart enough to set the source to the network card that actually can route to 102. It's pretty neat. I didn't even notice that like the first 50 times I did that, and then it just, like one day I was like, oh yeah, that kind of has to be that way because we need a route. In other words, because otherwise when the packet comes back, if that was still set to 127, then when it came back we wouldn't see it, right? So it's very clever. It's a really nice program. Okay, moving on. Well, we got an IP packet. It's pretty useless by itself because it's just a carrier. Let's put two packets together. So if we use the, I guess that's the /, it's the one on the bottom of the keyboard. And then let's add on a TCP packet. Now by default, if we do an ls TCP, we can see the defaults here in this column. Source port's 20, destination port's 80. No surprise, everybody starts with web, it seems like. That's the best bet for TCP nowadays. And then all your other options are available, including the sequence and the acknowledgement and so on. So if we do a show on our packet, let's look at summary first. So summary is another method you can call on your packets. It's It's a much more abbreviated version, but it's really nice, especially when you get your answer back. So we can see we have an IP packet to start that contains, as a payload of itself, a TCP packet going from 101.20 to 102 web 80. And the S means it's a send packet. And on TCP dump, if you're looking at these, remember that S is still, or send is still S in TCP dump, but I think the ACK is like a dot, but it's going to be an A in Scapy, so you can get mixed up pretty easy when you're sending the Scapy packets and then you're looking at TCP dump. We'll do that here in a minute to kind of watch for the dot. So, packet.summary. Now our TCP packet by default is actually going to be pretty good for this Windows box because it's already pointing to 80 anyway, so I'm just going to leave it. All right, sending the packet. That's going to be where this SR command comes in. So if we pass our packet to SR as an argument and we send it, it'll send the packet and then it'll listen for a response, and when the response comes back, it'll save it. It saves it by default into this pseudo variable underscore. So if we say like A equals underscore just to assign it to something, and then do like a print out A, we can see that the answered packets, it calls it results. We have one TCP packet that returned back to us. We have 0 UDP packets came back, 0 ICMPs, and 0 others came back. Of the packets that we sent out, they go over here in the unanswered area. We have 0 unanswered packets. So in other words, to summarize, we sent one packet of type TCP and we received one TCP packet back. That makes sense. Now if we do an a.show, oops, let's try a summary. Oh, I'm sorry, is it a, let me try this and then I'll explain it if it works. There we go. Okay. When the results came back into the variable underscore, I kind of failed to explain that they came back as an object, as basically essentially an array of lists. So list number 1, or number 0 in computer terms, is results. And list number 1 is unanswered. See the little comma between them? That's how you can tell it's an array. So now some Python programmer is probably screaming at the YouTube right now about how wrong I am about this nomenclature, but from my point of view, it's an array. I have no idea what Python really calls it. Maybe it calls it a list, as well. So, but because I can refer to results as 0 and I can refer to unanswered as 1, I think of it as an array. Now, within this array is 2 complex objects, and that's lists. So the results has a bunch of fields in it, essentially a list of fields inside of it. So that's why it was messing up earlier when I was saying a.show, it wasn't working because I was trying to do the show command on an object that has no show method. But if I drill down by putting 0, in other words saying I want the results one, I want to do the .show on the results, then that's why you have to specify 0. Now, by the same vein, we should be able to put 1 in there, and the .show, well, shows nothing because there's nothing to see. And maybe if we do it 2, it maybe even error out. Cool, okay, that's good. So that kind of confirms results is 0 and unanswered is 1. And there is no 2. All right, we could have sent the packet a little bit better to sort of avoid all this wrangling. So instead of saying just SR packet and then using that magic underscore variable to capture the results, we could have just set some variables up from the very beginning and made this a lot easier. So how about we do like answered for the first item, first list in the array that's going to come back, and we can say comma unanswered. And what will happen is when this array up here returns back it'll automatically place the first list in answered and the second list in unanswered. Does that make sense? So if we send that, now we don't have to kind of drill down into the return variable to get at what we want. We can just refer to the list directly as answered and say answer.show, or an alternative is to say answer.summary. Now the show command and the summary command, when you're looking at the packet you're constructing, are pretty different. The summary command is much more abbreviated output. But when you do the show and the summary command on the data structures that are received, that hold the received packets, they're actually pretty similar. There's not much difference between them, really. The only difference is this leading bit of data here. So they're practically the same thing. All right. Now we start doing some packet building, and we'll do, I think this is our TCP dump window. Yep, there it is. Let me try something here. Instead of or, there should be and. Can make a game out of this. Every time I make a mistake, just throw something at Adrian. What? By the end, you'll be wearing a football helmet.
Finally.
So. Okay. Let's do some packet crafting. It's good stuff. Actually, I'd rather not type all that again. How about if I just arrow up? So, we've got our packet ready to go. It's an IP with the TCP going to port 80. Got a TCP dump listing. This might even work. Let's send that off. And now we can see the TCP dump capture everything so we can look at it. So we sent to 102, see if I can find it. Oh, there it is. Let's kind of look at this line here. We sent from port 20 to port 80. Remember that send flag was set. So if we're doing host discovery, which is sort of the theme of all this, we want to pay attention to these flags. You notice in the packet that returned from 102 port 80 back to 101 port 20, there's a SYN ACK. So what's that tell you about the port?
It's working.
It's working, yeah. Or somebody's doing a really good job of faking everything, one or the other, right? Okay. So to get a confirmation on this box, though, if you're doing some testing for your customer, we think like the next packet you would send is.
You get a full handshake?
Yeah, that might be a good idea to figure out which service is running. So if you did like a handshake and what came back was, HTTP/1.0 or whatever, then it's probably a web server or some kind of web enabled device. Probably the next thing I would do is I would send on a port I think is almost guaranteed to be closed, and try to figure out if when we send it, if we're getting good results. So if I got a SYN ACK when I went to 80, if I send to say like 83, I should get like an ACK or a reset, and that can tell me if there's firewalls in the way or if I'm hitting the target directly. So in other words, is there something between me and the host? Is it going through something, or am I really talking to this host like I think I am? Of course, we can go back and use the Traceroute too, and that would help as well. But sometimes if your Traceroute to a good TCP port is like, say it was like 4 hops or whatever, but when you did the Traceroute to a closed port and it was only say 2 hops or whatever, guess where the firewall is, right? It's like on hop 2. So all this seems kind of random or arbitrary, but there's actually sort of a method to the madness here. We're trying to figure out what the architecture is and who it is we're really speaking to. Are we actually talking to like a web proxy? Are we talking to a firewall? What is it that's sitting on that border? Okay, there's an attribute of the packet called payload, And what it does is it tells you the payload of the very first Lego block. Okay, our first Lego is IP, and we stuck a TCP into that thing. So if we say packet.payload, it's going to give us a reference to the TCP. You know, you can do packet.payload.show or whatever, and so it's going to show us the TCP packet, just to kind of illustrate that point. So let's do packet.payload.destination port, which is D port. I know that because I copied it from right there. Is equal to 81. I don't put quotes around numbers in Scapy. So if you're saying the IP address is 192. whatever, put single quotes around it. But if you're saying the port is whatever, don't put quotes around it because that's an integer. So, and of course, the question should be, well, how in the heck do you know that? So, all right. So if you do the ls back on the TCP, see right here it says it's a short. And if you go look at the IP, oops, just type. It's this EMPH thing. I can't remember what that stands for. Ephemeral? Not sure. But anyway, it goes inside. It goes inside of quotes, and it even kind of tells you that it wants you to quote it up. Okay, so let's do packet.payload.dport is equal to 81, and do packet.payload.show. And so you can see that the destination port's 81, still coming out at 20, and the flag is still going to be a SYN. So everything else is the same. I'm going to send the packet. Okay, here we sent the packet. So we went from 101 port 20 to 102.81. We sent a SYN. Okay, so here's kind of the point of where we were going a minute ago. Do you notice what didn't happen?
You didn't get the SYN?
We didn't get any kind of information at all, right? It silently dropped the package. It's firewalled. Okay? So we just kind of learned something about the target by doing this. All right, let's go over to Windows. Get logged back in again.
You get the ACK on it, and Scapy uses the dot for the acknowledge, right?
The ACK in TCP dump is a dot, but the ACK in Scapy is an A.
Oh, is it an A?
Yeah.
Okay.
And it will mess you up too. If
I
you
kept shit on.
yeah.
Wait a minute.
I know. It's kind of, oops, sorry, general tab. Off. Okay. See if that changed anything. Different. So this time when we sent the Scapy packet, we sent, okay, so we sent it here. So 2080, port 81 with a SYN flag set, and look at the difference with the firewall dropped. So we got a reset flag plus also an acknowledgement flag, an RA. Okay. And we'll look at the packet a little closer. So we want to look at answered and .show. Because we did get an answer. And there's the packet we sent. Arrow means we sent it to. And then 102 on port 81 responded to 20. And there's the RA. Plus a little bit of padding on the end to make the packet come out even.
Can you disable that service name resolution so it doesn't say FTP data?
Oh, that's a good question. I don't know. Probably. You can do just about anything with this program. So I imagine you probably can.
We
But
should just go in there and wipe out the table to use it to translate it.
there's probably a setting or something. I don't know how to do it.
Now, how easy is this to plug into like your own Python scripts? You just have it automatically. I always want to send this kind of packet with just a couple parameters, so you package it all in one Python script.
Actually, it's pretty easy. One of the things that I was working on was I did the TCP handshake. So when the seek came back, I added one to it and put it into or wait, I can't remember, I get it backwards, but when one came back, I added a 1 onto it and then put it into my sequence. So I guess when the acknowledgement came back from the handshake, I added 1, put it into my sequence, and then set the acknowledgement and blah, blah, blah. Anyway, you can get the TCP handshake going. Because when you want to send web traffic, you have to do the handshake first, and then on your 4th send, you send the actual higher level protocol over. If you just try to send like web traffic before you've done the handshake, it's...
Does Scapy have a way of shortcutting that to where I automatically do the rest of the handshake for me and then let me get to the part I want to control?
Oh yeah, I'm not sure if Scapy actually had sort of kind of like a macro almost. Maybe. I actually just copied off Google's. I'll just admit it right now. I just copied off Google and I changed the parameters around to where I wanted them because somebody had already done a TCP handshake for some other reason. I can't remember. They were FTPing or something, and I just changed it around so it worked for web, and then used it that way. But yes, it really is Python, like it's running in a Python shell, so you can Python it all you want. And you can save save it off to a file and then run it as more like a script, instead of being interactive like we are now, just run it as a command script. So you can do that as well. So once you got things working, yeah, you definitely want to save them off because you can use them over and over again. Also, there's the SR loop, so you can do loops and stuff inside of Scapy, so you don't necessarily have to go to Python to get a loop going. There's loops built into the interactive shell that it has as well.
Fuzz function.
Yeah, we really just covered just the barest basics of just interacting with a simple port. But I do actually use Scapy at work to send some packets to some weird ports when I really want to try to figure out what's going on, when something's like doesn't make sense, or trying to figure out what it is that you're talking to. Now, I'll always fire off Nmap with the service discovery first because that's by far the easiest way to do it. But if it comes back with something really bizarre, then you can start sending individual packets with things changed just a little bit and figure out what's going on by interpreting the results. Okay. And then I kind of skipped a step. Let me turn the firewall back on Windows, back to where it was. I didn't really show the unanswered, but it works the same way. Okay, so let's repeat. All right, this is not going to work because the firewall's back up again. But we should be able to say, well, that packet should be considered unanswered. So we can do an unanswered.show and show the packets that were unanswered. And when you do looping, so if you say like answered, comma unanswered equals SR loop, it puts lists in answered and unanswered, and then you can run like show and summary on those lists, and it'll dump out like this packet made it, this one didn't, this one didn't, this one made it, and it'll keep them organized into the 2 separate lists between the packets that made it and got a response and the packets that didn't. A lot of intelligence built into it. All right, anything else we want to do with Scapy?
How do you set the flags? Is that just in the TCP part? Did you set flags to the other parameters?
Oh, yeah.
No, I see it there.
There's actually a function that'll let you even set the flags so that you can use the letters. I can't recall off the top of my head what the function is that translates the letters back into the bits.
Oh, okay.
So I'll just have to do it the hard way. So if we say like packet dot payload, whoa, that was weird. Wow, I just hit some magic button. That's like terminal just kind of vanished. Okay, let's try to figure out what that key command was. But that does come in handy. So let's set our basic packet back up. sequence attribute. Shows a method. So right now the flag by default, the default value for the flag is the send. So if we say, well, what is the value of flag? It should be, I think, 2 flags, sorry. So it's 2 because the second bit is set in the bit mask. So if we say, well, this is where it comes in handy to be a lot better at networking, because then you could actually remember where stuff is and always have to kind of fiddle with it. So if we do like a flags is, say 1 for example, that's going to set the first bit, but it's going to unset the second bit. Okay, that's not going to work. Well, it worked, we just got no answer. It actually told us a lot, but we got no answer. So let's go to TCP dump. Don't need that. Okay, so we send not the send flag, but the fin flag.
It looks like also when that top line where you did the IP destination equals and then added TCP to the end, looks like you just also in the TCP function do flags equal like SA and it sets it too.
Oh, yeah, that's true. You can do
Yeah.
sort of packet filtering based on flags. Actually, there was a person that gave a nice presentation at a conference last week, and they broke it down into incredible detail about
Oh, yeah.
some of the filters you can do.
Would be
And I think that's online at Adrian's site. Yeah, I can't remember the fellow's
Shoot.
name.
Probably John Ship.
John Ship, yeah.
Yeah, he was filtering by
It was the BPF
Like-
stuff, but it was crazy detail.
bits and stuff. That was, yeah, it was like, wow. All right, so let's change that flag to say like a 4. So it will be the 3rd bit from the right. Oh, I've got to send it again. Okay, so now we've sent a reset, and we can change it again, kind of see the pattern. Just keep messing, push. It's kind of neat how fast you can go through here and change these packets really easily once you sort of get used to the syntax, you know. And syntax isn't too hard. Okay, now this one's a little bit different, so check this out. So we sent a packet and we actually got an answer back. So before I flip over and figure out what it was, anybody want to take a guess at what position 16, position 5 is? So what kind of, other than a send, what can you send to an open website where the website's going to actually bother to respond to you? An ACK. So it should be an ACK. No, not captured. Let's see here.
You seen an act, what does it respond with a reset? If you didn't expect it?
Yeah. So you got an R there.
I'm sorry, I missed it because it's the dot. I'm looking for the A again.
Oh.
Did it to myself. Okay, so there's 101 port 20 sent to 102.80, the ACK.
Right.
And then 102.80 responds back to 101.20 with the reset. And that tells us basically that
Listening.
it's ready to go. It's listening. It's like, hey, that's weird. I don't recall seeing the original send, but I'm nice and I'll send you back a reset as a courtesy. So, all right. So that was, yeah, that's a good question. So we got some mileage out of that one. And then the remaining 3 flags are like those 2 weird flags that I can never have to do with quality of service and then urgent. We didn't do the 32. I think is urged or URG. Somebody else have a question? All right. So that's pretty good fun there with Scapy. You can have a weekend with that. That's a good time. Almost messed myself up on that. I got to studying for one of the exams and I got on Scapy and like stayed on for like a week. Got addicted. And I was like, well, I better stop doing this now and study some of the boring stuff. So Scapy's pretty good, and the Traceroute actually is really handy, the Linux one anyway.
Do that for CEH? Or you study?
It's either like, yeah, it's GSEC or GWAPT or one of those. I haven't done the CEH. I've taken the CEH videos or whatever, but never taken the test. Is there any other questions on crafting packets or?
If you were gonna complete the handshake, do you just, I mean, when you see that come back, I know you just change the acknowledgement number, but do you just do it manually? Is there a way to like, is there a way to like kind of hold the session in Scapy so it knows what's going on? Like it's smart about
Yeah,
it?
you can. So it's all Python, so you can write variables. So we could say like I don't know, like our sin is equal to 1 or something like that, and then so then in our packet. Packet.payload. I said rsin, I meant rseek. But anyway, you get the idea is that, so the packet.payload.seek is equal to rseek, and then you could do like, packet.payload.ack is equal to rseek, and then you could say like +1, and it'll automatically tack the 1 onto it.
Okay.
So you do need to write out like 3 or 4 lines of this, and then you send them all in at once, and then when the ack comes back, so you would say like answer.payload.ack, or you'd say rsin is equal to answer.payload.ack +1, and that goes into rsin. So you can take the result back from the answered variable, at least what I call it answered, you can call it whatever you want, and feed it back into the packet variable for the next SR.
That's good.
Yeah. That way you can do conversations.
Right.
And that's exactly how you do the web handshake, so that you can go ahead and send the, like, you can send like a get root or whatever, and build, a very rudimentary, essentially something just to figure out what the options are on the web server or something like that. Of course, in reality, you would end up using like Netcat,
Right.
because it does the 3-way handshake automatically. But so this is pretty much, I think it can do a lot of what like Netcat can do, but it's doing it at a much
I guess you can do
lower
anything,
level.
really.
That's true.
Creating the packets.
You're building at such a low level that you can do just about anything you want. But of course, it would get impractical to do common tasks.
Yeah.
But if you wanted to change a task slightly, this would be the answer. So if you can't figure out a way to do it with the software you have, you can always come here and construct it yourself. That'd be kind of interesting to build like
A web server?
a web server or something out of Scapy. I'm sure you can do it. Some kind of loop and just listen and respond, listen and respond, listen and respond. But I think most people just go with Apache. So the value is being able to control the minute details and then get the answer back and take the answer apart, in the slightest slice to figure stuff out.
Does it work with version 6?
Oh yeah, we didn't look at that, but let's see. So let's say it'd be like packet dot. It wouldn't be dot payload because that would be in the IP. So it'd be the very first label block we happened to use, which was IP. And so packet dot. I'm trying to remember. Is it IH or something like that? Let's see. Let's look at the. Let's do a dot show, which really shows the gritty details. Oh, I'm sorry, it's version. Yeah, IHL is something. So the version was 4. Okay, so now the version is 6. I think it works with IPv6. I know there's some other things that you have to change too, because the actual IPv6 packet doesn't look like exactly like a 4 packet. The fields are rearranged, and it's also much simpler. The 6 version is way simpler than the 4 version, although there's this options area at the end of the 6 packets where you can put just about any kind of configuration, so you can, it's much more extensible, but at the same time it's much simpler. It's kind of cool. Of course, the IPv6 has the, I think, source and destination first, and they're real long, so they're 28 bits or whatever.
I know I've been checking it out between my phone's a Wi-Fi phone.
Mm-hmm.
So I get at home, I'll do some testing against the phones.
Yeah, that's fun. So was it enabled by default from the factory?
No, it's what it runs on.
Oh, okay.
It
So
doesn't use V4 at all.
oh, okay. Well, that's pretty interesting. Is it an advanced phone? Or is it normal?
This one,
Alright. Good stuff. Yeah, I think most of the Linuxes now, when it just starts up, like Ubuntu for example, it'll talk on 4 or 6. It doesn't really seem to care one way or the other. So you could probably generate some IPv6 traffic pretty easy. Of course, TCP dump, we didn't really talk about how to use that because we covered it the last time around. So if you have any questions on TCP dump, if you didn't make it last time, just let me know. But it's pretty straightforward. We're just capturing the packets so we can analyze them a little bit easier. All right, good stuff. So 2 o'clock, so I guess we'll wrap it up here. And next time will either be more host discovery or probably looking at some service discovery and some higher level protocols, web and stuff like that. We need to get to the point to where we can start turning up a web server. So.